Yes, ma'am.
Today we are going to see about the knapsack problem using dynamic programming. About knapsack problem, we've already seen in the last class, a little bit in the last class. So this particular topic is from your textbook, that is the first textbook, Introduction to Design and Analysis of Algorithms, Anani Levitin, from page numbers 284 to 288. Uh, Now, this is what we learnt in the last class, right? We saw considering the case where n is equal to 3 and m is equal to 6. N is the number of objects and m is the maximum capacity. And these are the weights and profits of the objects that are given. We have to compute G0 of 6. Now, this is a top-down approach which was used for computing the optimal solution. Okay, G0 is basically the optimal solution which we want to find out. Now, for computing G0 of 6, we had to basically find out maximum of G1 of 6 and G1 of 6 minus 2 plus 1. In other words, G1 of 6 meaning the first object is not selected at all. And the G1 of 6 minus 2 plus 1 means the first object is selected. So the remaining capacity becomes 6 minus 2, which is the weight of the first object, and plus 1, which is the profit that you're earning from the first by selecting the first object. Okay, so then again G1 of 6 we need to compute. So when we are taking G1 of 6, then that means G2 of 6 and maximum among these two. That is not selecting G2 and not selecting the second object and selecting the second object. So when you're not selecting the second object, if you want to find out for G2 of 6, then it is G3 of 6 and selecting the third object. But if you see over here, G3 of 6 will be 0 because when you're talking about G3 of 6, that means none of the three are selected. Okay, so if there are none of the objects are selected, automatically the profit that is earned will be 0. So maximum that value becomes 0. And if you take G2, G3 of 2, now if I am telling G3 of 2, basically that means 2 minus whatever value has to be there, but there are no other objects. So third object is already selected and my weight has become 2, but then there are no other objects that I can select. So basically if you are going to find out of G3 of 2 again, it will become 0. Okay, so 0 plus 5 will give me 5. So maximum of 0 and 5 will give me 5. So G2 of 6 I found it as 5. That value will be given over here. So next thing I need to compute this side, that is G2 of 6 minus 3, that is 3. So G2 of 3 if I have to compute, then basically I'll have to compute again like, can someone mute? If you guys don't have doubts, please mute. Okay, so G3, G2 of 3. Now maximum of G2 of 3 will be G3 of 3 and if I'm selecting the third object. But if I'm selecting the third object, the problem is weight is more than the maximum capacity, the available capacity. So G3 of 3 if I have to take, G3 of 3 again will be 0 because that means I have not selected any of the objects again. And weight of the fourth object is basically greater than whatever is already there. And if this basically becomes a negative value, and since weights cannot be negative, we have to consider it as minus infinity. And between 0 and minus infinity, maximum value will be 0. You can either consider it as minus infinity or you can consider it as 0 itself. Okay. But if you're going to consider it as 0, the problem is plus 5 will become 5. So we cannot basically consider this part. You cannot have a negative value. That's why we are considering it as minus infinity. So anything added with minus infinity basically will be a very less value compared to the other one. So this way we have to try to we find out for the lowest value. Now once we have this as 0 and this as 5, then between 0 and 5 we need to find out which is the maximum. Take that and put it as G1 of 6. Again you have G1 of 6 minus 2, that is G1 of 4. We need to find out for G1 of 4 again. So like this the process goes on and finally we go to the top. But one thing that we can see over here is the problem with top-down approaches. If you're gonna go on doing it, it becomes similar to your divide and conquer approach at times. Okay, so dynamic programming, knapsack programming using dynamic programming, if you're talking about, We said in dynamic programming, you have to solve all the problems once, keep it in memory, and if in case it has to be used again, we will try to use it again. So just generalizing the knapsack problem again, you are given with n items with weights w1 to wn and profit values as v1 to vn. Maximum capacity given as w. Over there we took it as m, here we are taking it as w. We need to find the most valuable subset of items knapsack. So here, using dynamic programming, we also call it as 0 bar 1 knapsack problem. So it's either you choose or you do not choose a item. Okay, so the goal is to solve the knapsack problem using dynamic programming. So in dynamic programming approach, to solve this knapsack problem, we need to come up with one set of instances, bottom-up approach. Okay, so in the bottom up is okay. Let's consider. We uh, we said we can try from the first till the intermediate node, and then from the intermediate node again we can try to go till the end. So let's say we have some intermediate value I. So consider an instance defined by first I items. In all the n items that we have, let's say we are taking for the first I items. We'll have weights as W1 to Wi, profit values as V1 to Vi, and the maximum capacity we're going to take it as J. For that particular value, we are going to take it as J. So optimal solution basically will be present at the position V of I comma J. That is, I is the ith element. Till the ith element, all the elements have been checked whether they can be chosen or not. And J is the capacity that we are trying to take at that particular instance. So the approach that we are going to take is we are going to divide the first I items into two categories. The first category will be those that don't include the ith item, and the second category will be those that do. So if this is the case, how do we go about? So dynamic approach using knapsack, possible cases basically will be you have your value of j which will be less than the weight of the ith item. So if it is less than the weight of the ith item, then we cannot include the ith item. But if it is greater than the ith item, we can basically include the ith item. Yes. So if it is greater than or equal to wi, then we can include that particular item. So these are the two possible cases that you can have. And when will it be less than W of I? Yeah, J will be less than W of I if in case if I'm going to add this W of I, J minus W of I will become less than 0. Okay, now let's say J is 2, W of I is 4, then 2 is less than 4. So if I think of adding 4, 2 minus 4 becomes minus 2, which will be less than 0, so I cannot include it. Whereas if J is 4 and W of I is also 4, then 4 minus 4 becomes 0. So I can actually include that particular value. So this is the formula that we will get when we are trying to use this dynamic programming approach. That is two cases. If I'm including the ith value, j minus wi, if it's greater than or equal to 0, then basically I will take the include that particular object into my knapsack. If it is less than 0, then I'll basically not include that particular object into the knapsack. Now, if I don't include the ith value, my j will remain as it is. Yes or no? If my j was 2, and say wi is 4, I am not including the ith item. Then basically j will remain as 2 itself. It doesn't change. So it will be whatever value that I had previously for when I had selected the previous element. So the profit that I got at that particular point of time only will be taken as it is. Okay. But in case if I am selecting, now j is 4 and w of I is also 4 and I am selecting it, then basically I have to see if the previous value, whatever I had, that value, and when I'm choosing the new object also, if my profit is increasing or not. So I'm checking maximum among the previous value and the profit of the current object plus whatever profit was there previously when I had j minus wi. Okay, now j value is 6, minus wi will be 4. So 6 minus 4 is 2. So what was the capacity of I minus 1 comma 2? So if I go for that particular profit, that value and the current profit of the current object. If I'm adding between these two values, which is the maximum, we can choose that. Now, just by looking at this formula, it is a little bit difficult for you to understand. So let's see how this formula works so that we can understand it very clearly. So in order to make it more simpler for us to understand, we are going to follow a table approach, table method, wherein we are going to tabulate all the values for all the elements, and then finally we will be able to basically get the optimal solution. So if I'm telling v of I comma 0, I'm going to make v of I comma 0 0, meaning I is the element object, okay, and 0 is the total capacity. Now if I'm telling the total capacity is 0, that means I cannot add any of the objects inside, so definitely my total profit will be 0 no matter how many ever objects I have. If the capacity value is 0, my total profit basically is going to be 0. The other cases, if I don't have any objects but I have some capacity in my knapsack, still the profit that I am going to earn will be 0 itself. So what we are going to do is we are going to tabulate it. So in the tabulation, you can see that all the initial values will be 0. Starting from the 0th object till the nth object, if the capacity value is 0, then basically all the values profit earned will be 0. Same way, if there are no objects, no matter whatever is the size of the capacity, all the values will be 0 itself. Now, let's say we check for some one condition, that is v of I comma j. I want to find this particular value. There are two ways in finding out this particular value. One is I am choosing this ith element. The other one is I am not choosing this ith element. If I do not choose this ith element, then basically this is the value that I will have to take and put. That is the previous value. Yes or no? I minus 1 comma j. So I will basically choose that as the first value v of I minus 1 comma j, and I will put that in the same place of v of I comma j. Meaning I am not choosing the ith element at all. But if I include the ith element, I told you if the value is wi, then I have to go to j minus wi'th position. J minus wi'th position in the previous row. So that means I have to come to this particular location. This, supposing this is j minus wi'th position, then I minus 1 and j minus wi, this is the position I have to come. Take this value over here, okay, and add the current profit of the ith element to this particular value to get the current value. That is what our formula basically suggests. So this is okay. So the value of optimal set will be vi, that is the profit of the ith element, plus v of I minus 1 comma j minus wi. You understood this part? Yes? Okay, so let's just take an example and see how exactly this particular formula of ours works and how we can do it using the table method. Now consider an knapsack of size 5, and maximum weight it can hold is also 5. That means your capacity, maximum capacity is 5. So weights given to you are W1 is 2, 1, 3 and 2. And the values are profit of the first object is 12, second object is 10, third object is 20 and fourth object is 15. Now what we have to do, we have to find the maximum capacity. Now the total value is 5. That means there are 3 different options in which you can choose, right? You have 2, 1 and 2 which you can choose. You have 2 and 3, 3 and 2. These values also you can choose. So you can have 3 different subsets which basically satisfies the criteria of having the maximum weight of 5. But then among these 3 subsets, which will give me the maximum profit is what we have to see. Now if I take 3 and 2, you get 20 plus 15, that is 35. Whereas if you are taking this 2 and this 3, you get 12 and 20, which is 32. So if I take 2, 1 and 2, that is first object, second object and fourth object, if I choose, I get 12 plus 10, which is 22, plus 15, which will give me 37. So I find this as the best way of choosing. So when you do the dynamic programming approach, at the end you will always end up getting the optimal solution at any cost. So this is the table we are going to do, that is starting from the 0th object till the 4th object, starting from 0 kg till 5 kg. So the capacity. So if you're given, say, W as 7, then you'll have to have 7 columns. Okay, sorry, 8 columns. Okay, 0 to 7. And if you're given 6 objects, then 0 to 6, you have to have so many rows. Okay, so initial condition is when we are finding out for V of 0 comma j. J is this, correct? So all the values will be 0. Then you have to do I comma 0. Yes, so the I comma 0 is also 0. That means all this column will become 0. Next, now we have to find out for this position, that is V of 1 comma 1. So V of 1 comma 1, I can tell it as I minus 1 comma 1. So I minus 1 is 0. So 0 comma 1 is 0. I can take that value as it is. So this will become 0 here. And then the other value that I can think of choosing is, I can try to find out if I choose the first object, that is weight 2. But then if I take weight of 2, this is less than 2. 1 is less than 2. So I cannot choose W1. So automatically I will take 0 itself. It will go to minus infinity. So between 0 and minus infinity, 0 is the option value I am choosing. Now next is V of 1 comma 2. That means now I am telling I have only one object and I'm going to choose for all the capacity. Okay, so with one object, with all, for all the capacity, if I have to choose, I have to find out for V of 1 comma 2, 1 comma 3, 1 comma 4 and 1 comma 5. When I come for 1 comma 2, I find the weight is 2, capacity is also 2, meaning I can choose this particular value. Yes, so between V of I minus 1 comma 2, that is this position, that is 0, and this particular position wherein I am choosing this object, so I'll get profit of 12 plus the previous value. 0 of 2 minus 2 is 0. So 0 comma 0. What is the value of profit plus this value? Okay, so if I add, I'll get the value as 12. So that is the value I'll be adding in the table. Next, I need to find out for 1 comma 3. Okay, so when you find out for 1 comma 3, it will be 0 comma 3, which is I minus 1 comma j, and 0 comma, that is I minus 1 comma j minus wi. J is 3, wi is the current value, which is 2. So 3 minus 2 is 1. So I go to this position, take this value and add with it. So again 0 and 12 basically will give me 12 itself. Okay, so same 12 gets added. Same way for 4 and 5 also, you can work it out, you will get the same values. Okay, because all the previous values are 0. If I take minus 2, okay, this particular position minus 2, because the weight is 2. If it was 1, then minus 1. Okay, so now V of 2 comma 1, next is 2 comma 1. If I go for 2 comma 1, the weight is 1, and here I am telling I minus 1 is 1 comma 1. Okay, that is I minus 1 comma j. J is 1, so 1 comma 1, and I can also include this particular value. So it becomes, if I include, what it will become. So I minus 1 will be 2 minus 1, which is 1, comma 1 minus 1 is 0. So 1 comma 0 is this particular position. Okay, so I go for this particular position value plus the profit of this object, that is 10. So 10 will be the value that I am getting, because 1 comma 1 is 0 and 10 plus 0 is 10 itself. So maximum value I'll get it as 10. So that is the value I will put over here. Now when you come to this position 2 comma 2, what do you think will happen? Okay, 2 comma 2 is maximum of 1 comma 2, that is 12. And if I choose this particular object, so if I choose this object, 2 minus 1 is 1. So 1 comma 1, I have to go to V of 1 comma 1, which is 0. So 10 plus 0 gives me 10, and this value is 12. So 12 as it is I have to take. If you can see, between the two values, whichever is the maximum, I am choosing and I am putting that as the optimal solution at that particular ith position, I comma jth position. Again, next I have to come over here. When I come over here again, I'm trying to find out the same way. 3 minus 1 is 2. So between 12 and the previous value, that is 12, 12 plus 10, 10 for this profit, and the previous value which is 12. Between that, which is greater, meaning 10 plus 12 is 22. So 22 becomes greater. So the new value here becomes 22. Meaning I have selected, when the capacity is 3, I have selected both weights 2 and weight 1. Okay, both the objects have been selected, and hence my profit basically becomes 22. Okay, and when you're going for the fourth position, again I would have said the same thing continues. It will be 22 itself, and 5 also, it will be 22. Here I find I could select only the second object. When I came here, I found I could select the first object instead of the second object. When I came to the, when my capacity became 3, I found I can select both the objects, and I found the maximum capacity. Now, when I come for the next thing, wherein I am trying to tell I have 3 objects which I can have, but the capacity of my bag is only 1, meaning I can choose maximum only the second object. Yes or no? So basically, I'll get 10 as the value. When I'm coming to 2, I find that this is the maximum value I can choose. So basically, it becomes 12. Okay. So you can see it will become 12. When I come to the third position, that is 3. Now I have 3 options. Either I can choose this, or I can choose this. Both will give me 3. This is also 3. 2 plus 1 is also 3. But between these two, I find 22 is greater than 20. Yes or no? So that is how we work it out. So if you see, maximum of V of 2 comma 3, which is the previous value, and 20, which is the profit of the current object, plus 3 minus 3 basically is 0. So 2 comma 0 will give me 0. So 20 plus 0 gives me 20. So 20, between 22 and 20, I find 22 is the maximum. So that is what I will choose. So if you see at each step, whatever is the optimal value, that is what we are choosing. So finally, if we keep proceeding the same way, next if you see here, 4 minus 3 is 1. So that means 3 plus 1 is 4. That is what I am choosing. So that will give me a value of 30 as the profit, comparatively to the previous value which was 22. Now I've got 30 as the profit which I can choose from. Then if I take the fifth value as 5. Now among this I have 3 plus 2 which is 5. So which will give me 20 plus 12 which is 32. So I can basically choose that as my next value. Okay. Then if I take for the next one, 4 comma 1, I have all 4 objects, but I have only 1 as the capacity, meaning it will be only this object that is chosen. So it will remain 10. When I tell it is 2, then I can now either choose this or this. So between 12 and 15, it will find 15 as the maximum value. So it will basically choose that as the maximum value now. Till here it was 12. Now it became 15. Okay. Now again I'm going to choose the, I'm going to increase the capacity by 1. So it becomes 3. So among 3, I can either choose this or 2 plus 1, that is 10 plus 15, which is 25, or 22. So between 20, 25 and 22, we find 25 is the maximum value. So that is what we are choosing. Then next we find for 4 comma 4, it will remain as 30 itself. And for 5, now we find the best option, which is okay, for 5 we have to find out 5 minus 2, that is 3. So when j is 3, it has to come to this column, and I minus 1 is 22. So 22 plus 15 automatically will give me 37. This and this indicates that I've chosen these two objects. Okay, so I get 37, which is the maximum optimal capacity. So if you want to find out the optimal solution, it will always be present in this last value, which is the n comma mth position. Okay, or n bar w.